Hello everyone, welcome to this lecture on NumPy. If you are diving into data science, machine learning, or scientific computing, NumPy is your best friend in Python. NumPy is an open source Python library. It was created in 2005 by Travis Oliphant as a successor of Numeric and NumArray. Its goal was to provide a powerful tool for numerical computing. NumPy serves as the foundation for scientific computing in Python. It offers a high-performance multidimensional array object and a wide range of mathematical functions to operate on these arrays. NumPy's core functionalities like linear algebra operation, Fourier transforms, random number generation, and efficient element-wise computing help us to do many things. That's why NumPy is excellent for data analysis, machine learning, and scientific research. Its ability to handle large data sets with speed and integrate seamlessly with other libraries like SciPy, Pandas, and Matplotlib has cemented its role as a cornerstone of the Python scientific ecosystem. In this lecture, we will explore every major Python feature, from creating arrays to Fourier transformers with several examples. Whether you are a beginner or pro, you will learn something new. Grab your code editor and let's get started. First, let's create arrays, the core of NumPy. Arrays are like Python lists, but they are supercharged for numerical tasks. We import NumPy and we can change it with, like, for example, np, the name for easier access, and we use np.array to turn a list into 1D array. For 2D arrays, we use nested lists, for example, matrices. NumPy offers np.zeros and np.ones for arrays of zeros and ones, and also np-arange for sequences, np-linspace for evenly spaced values, and npi for identical matrices. So let's try. The first thing that we need to do here, we need to import NumPy as np. So we already imported this one. And if you didn't install it, simply here pip install NumPy, right? In this way, we can install it. So I already installed this one here. We're gonna convert some Python list to NumPy array. For example, array1 is equal to, so we're gonna call this function instead of NumPy, because with some alias, just we call np.array, and for example, 1, 2, 3, 4, 5, right? Then here we can print our array as this one. So let's try this one. So this is 1, 2, 3. This is the array that we have generated. We can get the shape of this array. For example, print arr1.shape. It means this is a 1D array, one dimension array with 3 elements. If I change this one for 4, and if I get the shape, it will be 4. It means 1D array with 4 elements, right? Also, I can print the type, right? So print array1.dtype, and if I execute, it gives me integer 64, right? Then I'm gonna create one 2D array, right? So arr2 is equal to np array 1, 2, 3, 4, right? This is a 2D array. So this one, if I print this one, print this array, then I will get something like this one. And if I print the shape of this array, print shape of this array, then you can see it will give me 2 and 2. 2 lines, 2 rows, 2 columns, right? And if I print the type of this array, I will get integer. As I said, NumPy gives us some specialized array creation as well. For example, I want to create one 2 by 3 array and all zeros, right? So for example, zeros is equal to np zeros 2 and 3. Then this one you can see here, it means 2 rows, 3 columns, and all with 0. Or the same thing I can do for ones, right? For ones is equal to this one. Ones is equal to np.ones 2 and 3, and here print 1. It means I get one matrix or to the array, and in here everything is 1, right? And this is 2 rows and 3 columns, right? Then I can create an array with values, for example, 0 to 9, and with a step of 2, right? For example, I can say range underscore array is np range of, for example, 0 to 10, and the step size is 2, right? Then if I print this one, you can see here, it will be something like this, 0, 2, 4, 6, 8, right? So even numbers. And if I change this one to, for example, 3, then it will be 3, 6, 9, right? So this is the starting. So if I change this start to 2, then you can see here it will be 2, 5, 8. So 2 plus 3 is 5, plus 3 is 8, right? The start point, end point, and step size. So if I change this on to 100, then you can see here, these values I can get 2, 5, 8, 11, 14, something. The next thing is the lean space that we use a lot. So the lean space is a little bit different. We create some evenly spaced values in a range, right? So let me show you, for example, lean space array is equal to 210, right? It will start from 2 and it will goes to 100, and in this between it will generate 10 numbers, right? So you can see here from 2 to 100, 10 numbers has been generated. This is different by this one. In here we go from, so if I change this one, for example, to 3 to see the difference. So in this one is we get from 2 to 10 and by a step of 3. But in here we go to get only 3 numbers from 2 to 100, right? So between this range of 2 and 100, it will give me 3 numbers. Or for example, if I say from 0 to 10 and give me, for example, 100 numbers, right? So here you can see 100 numbers generated between 0 and 10. We can see these numbers are here. We use these things a lot in machine learning and data science. Or, for example, I want to create a 3 by 3 identity matrix, right? So I underscore array is np.i3, right? So you can see here in this array, every element is 0 except I and I, right? So 1 and 1 is 1, 2 and 2 is 1, 3 and 3 is 1, the rest are 0, right? So this is called as I matrix. It doesn't matter the size. If I change it to anything, so then it will give me all by this one. So in here we get 8 by 8. Now I want to change the size, right? I don't want to be 8 by 8. I want to be 8 by 7 or 8 by, for example, 3, right? So you can see here we get 8 rows and 3 columns. So in this case, when I get 8 and 3, then you can see here 1 and 1, 2 and 2, 3 and 3. The rest are equal to 0. In here also we have something k is equal to 1. So when k is equal to 1, so let me change this one to 8. So when it is 1, it starts from 1. You can see here the first one is not 1, right? By default it should be. So if I remove this k equal to 1, this is the position of the first one. So you can see here the first element here is 1. But if I change this one to k is equal to 1, then the second element is equal to 1, and you can see here it will be something like this. For example, if I change this one to 2, then the third element will be 1. You can see here, and then it goes like this. The next topic is array indexing and slicing. This help us how we can access array elements. Imagine we have a 3 by 4 array as a grid. We can access the element here. For example, I have one array, so array is equal to np array, and so let's add some more values here. For example, 4, 3 and 4, 3 and 4, then here 5, 6, 7 and 8, then here I will add one more, 9, 10 and 11, 12, right? Then we can print this array. So here it is. We have a 3 by 4. So we have 3 rows and we have 4 columns. Now I want to access some elements, right? So for example, I want to access element at row 1 and column 2, right? So array, then here I will pass 1 and 2. So you can see it's 7. If I add print here, so you can see here the 7 is a 1. In here we start from 0. So we say row number 1. So row number 1 is this row, and column number 2, column number 0, column number 1, column number 2. So this is 7. If I add for 0 and 0, then you can get 1. So 1 is 0 and 0. If I add 2 and 3, then I will get the last digit, 12, right? Here, 12. I can also slice first row. So if I want to get only the first row, so print, then in here, I want to get array, this array that I have defined here, and I want to get from 0 and here the rest, whatever it is, right? So it means the first row, 1, 2, 3, 4. If I want to get the second row, simply second row, I should add 1 here. So this is the second row. And a third row, I should add for third row, right? So this is the third row. Or if I want to go for the columns, a little bit different. So in here, I should add column and then here 0. So this one, it will be 159, right? 159, the first column. Or if I add this one here, then I will get 2, the second column, right? 2, 6, 10. If I want to get, for example, in here, if I want to get the row from 0 to 1 and column 1 to 2, right? A slice. So I want to get from 0 to 2, right? And for the columns 1, 2, 3. So you can see here. So this is a portion. So if I print that one, so this is our original one, and rows from 0 to 2, 0 to 2. The last one is not included. If I add 0 to 1 here, then I will get only the first, right? So if I want to go, so 2 will not be included, right? So it will be first and second one. And column 1, so this is the 1, 2, 3, the second one, right? So if I get this one to 4, then I will print the rest, right? 2, 3, 4, 6, 7, 8. For example, if I want to get this 6, 7, 10, 11, right? So for this case, I should go from 1 to 3, from 1 to 3, and this one from 1 to 3, right? So this will give me 6, 7, 10, 11, right? In this way, I can print it. Next, I want to try some Boolean indexing, right? So we create Boolean array where true if element is greater than 5, right? So for example, mask is equal to array greater than 5, then we will print this mask, right? So you can see here, if it is greater than 5, so let's print our array again, right? So 1 is not greater than 5, it's false. 2 false, 3 false, 4 false, right? 5 false, not greater, so equal is not here. So false, but the rest are true. 6 greater than 5, 7 greater than 5, 8 greater than 5, and etc. So for example, if I add one equal sign here, then this 5 will be true as well. If I change this one to less than 5, then you can see it will be opposite side. True, 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 right? 1, 2, 3, 4, and the rest is false. And then here we can try to select elements where mask is true, right? So we can print, for example, array and mask, okay? So let's see here, only true will be printed. The rest will not be printed, right? So if I change this one, then here you can see this one, false, 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 and the result is those are greater than 5, 6, 7, 8, 9, 10. We can try array of indices for row. For example, indices equal to np.array. And in here, we have an array of, for example, 0 and 2. So in here, array indices. So let's see the result. So in this way, we can access rows 0 and 2 only, right? Row 0 and 2. You can see here 1, 2, 3, 9, 4. So if I change this one, for example, to 1 and 3, then you can see here we have no 3, right? So let's change it to, for example, 1 and 2. Then you can see second row and third row. Here we can make row indices. For example, row underscore indices is equal to, for example, 0 and 1. And we can add column indices as, for example, 1 and 2. Then we can print array row indices and column indices, right? Specific rows and columns that we have decided here. It will be 2 and 7 based on 0, 1, and 1 and 2. So in here, what we are going to access is the element 0 and 1. Element 0, this is row 0 and column 1, right? So it is 2. The second one is row number 1 and column number 2. It's 7, right? So the output is 2 and 7. NumPy arrays shine with element-wise operations. We have some universal functions like sqrt, sum, min, max that we can apply for calculation across arrays instantly. So let's try some of them. So for example, we have A as an NP array of, here we have 1, 2, and 3, right? Then we have B as NP array of 4, 5, and 6, right? Now I want to print array 1, so print array 1 simply. We can try this one. So array 1 is 1, 2, 3, or we can print in another way, for example, print, then in here, array A is this one, or array B is this one, right? So array A is 1, 2, 3, array B is 4, 5, 6, right? Now I'm gonna add some element-wise addition, right? It means A plus B. So element-wise addition is A plus B. So let's try this one. So 1 plus 4, 5, 2 plus 5, 7, and 3 plus 6 is 9, right? Or I want to multiply array number 1 with 2, right? So we can call it as a scalar multiplication, right? Scalar multiplication of A multiplied 2. So each element of A is multiplied by 2. So 1 multiplied 2, 2, 2 multiplied 2, 4, 3 multiplied 2, 6, right? Or I can apply square root to each element of A. So print, then here is square root of elements, right? Root of elements, and in here I will call a function called that sqrt, np sqrt of A, right? So you can see here, the sqrt of 1 is 1, for 2 is 1.4, and for 3 is 1.7, right? Or I can print a square, right? Print square of elements of A power of 2. So 1 power of 1, 2 power of 2, 4, 3 power of 2, 9, right? I can go for element-wise multiplication, right? It means each element of A multiply B. So 1 multiply 4, 4. 2 multiply 5, 10. 3 multiply 6, 18, right? Or I can go for element-wise division, right? Each element of A divided by B. So A divided by 4.25. 2 divided by 4, 5.4, 3 divided by 6.5, right? Or I can go for example, element-wise power, right? Each element of A in power of 2. So 1 in power of 2, 2 in power of 2, and 3 in power of 2 as 1, 4, 9. I can use some universal functions, for example, print. In here, I want to get sum of element in A. So sum of element in A is equal to np dot sum A. This is a function, and I will calculate the sum of all functions in array 1. So you can see here, 1 plus 2 plus 3 is equal to 6, right? Or I want to find the mean of, it means the average of the elements, right? So mean of elements in A is, so the mean of element in A is np dot mean. This is a mean. So it will pass all the elements of A here and it will calculate. So 1 plus 2 plus 3 is 6 divided by 3 is equal to 2. So you can see here mean of element is 2, right? Or I can find the maximum one, right? So in here, for example, max of A. So what is the max of A is np dot max, right? So all elements will go here and the maximum one will be selected, which is 3. Or I can try, for example, mean of the elements in A, the minimum value, right? It is 1. These are called as universal functions. Now we're gonna try some array manipulation. It's time to reshape arrays. We use a reshape function to change dimension, like turning a 2 by 3 array into 3 by 2. We can use flatten to collapse an array to 1D, and we can use transpose to swap rows and columns. We can concatenate arrays with H stack for side-by-side or V stack for vertical stacking. These tools are key for preparing data for analysis and machine learning. So let's try one array, and this array is, for example, 1, 2, 3, 4, 5, 6. So this is the original array, and in here we're gonna add array. So let's see our original array, comma should be here. So the original array is this one. So let's add one \n here. So original array is 1, 2, 3, 4, 5, 6, right? Now I want to reshape this array. So what is the shape of this array? Array.shape. The shape is 2 by 3, 2 rows, 3 columns, right? Now I want to reshape it, right? So reshape underscore array is equal to array dot 3 by 2. So it's originally 2 by 3. I want to change it 3 by 2, right? So you can see here, I change it. This is 2 rows, 3 columns. In here, 3 rows, 2 columns. I can flatten array. So an array can be flattened to 1D, right? So flatten is equal to array dot flatten, right? And then we can print it. So you can see here 1, 2, 3, 4, 5, 6. It's 1D array with 6 elements. Or I can transpose, right? I want to swap rows and columns, right? So transpose is equal to ar.t. This t will transpose my array. So I can here print the transpose array. So here we go. So in here, the original array was this one, right? The original array is 1, 2, 3, 4, 5, 6. But now it's 1, 4. You can see here, the first column becomes the first row. The second column becomes the second row. And the third column becomes the third row. This is called as transpose. Or I can go for concatenation. It means I want to horizontally concatenate 2 arrays, right? For example, array 1 is 1, 2, 3, 4, and array number 2 is 5 and 6, right? Then I want to horizontally concatenate, right? So concat underscore h is equal to, we use np.hstack, right? And this will horizontally concatenate these values. So you can see here, 1, 2, then 5 and 6, the first row of the second one came here. And 3, 4 was the second row, and the second row of the second matrix has been added here, right? This is called as horizontally concatenation, right? Or I can do the same thing for vertical concatenation. So concat underscore v is npv stack array 1 and array 2. So you can see here 1, 2, 3, 4, 5, 6, 7, 8, right? It has been vertically concatenated. So the original one was this one, right? Original one was 1, 2, right? Then 3, 4 become the second row, then 5, 6, then 7, 8, right? This is horizontally concatenation. NumPy is a beast for linear algebra. We can multiply matrices with the dot function, we can compute the determinant, or we can find inverse. We can get eigenvalues and eigenvectors, or we can solve linear system with linalg.solve. These operations are vital for physics, engineering, and machine learning, and NumPy makes them effortless. So we have these two arrays already now. So this is a 2D array, so that's the matrix, right? So I want to do some multiplication between A and B because we have already two matrices. This array 1, so let's print array 1, print array 1, right, and print array 2. So we have already two matrices, right? These are two matrices or 2D arrays, 1, 2, 3, 4, 5, 6, 7, 8. Now I want to do matrix multiplication, right? So print, and here np dot array 1 and array 2. This is a kind of matrix multiplication, right? It will be 19, 22, 43, and 50, right? How we do this multiplication? So how this works, this multiplication? So what we do here, the first row of the first matrix multiply the first column of the second matrix. 1 multiply 5 plus 2 multiply 7, right? The first row multiply the second column. 1 multiply 6 plus 2 multiply 8. Then the second row multiply the first column. 3 multiply 5 plus 4 multiply 7. Then the second row multiply the second column. 3 multiply 6 plus 4 multiply 8, right? And here we go. It is the same, 19, 22, 43, and 50. Or we can find the determinant, right? So print np dot, in here we go for submodule, right? linalg dot determinant of, for example, array 1, right? So it is -2. So we already know that the determinant is equal to AD minus BC, right? So our array, our matrix is this one. So the determinant is equal to A multiply D. It means 1 multiply 4 minus 2 multiply 3. So A, this is A, B, C, D, right? A multiply D, B multiply C. And if we print it, it will be -2. Then we can try to find the inverse of a matrix, right? Print, and in here again np dot, this linalg is a submodule in NumPy, right? linalg dot inverse, this function for calculating the inverse, array 1, right? So we can print it in this way, -2, 1, 1.5, and -0.5. So our matrix is 1, 2, 3, 4. How to find the inverse? Inverse is 1 divided by determinant multiplied D minus B minus C A. So here we need to find adjoint of array 1. Array 1, so adjoint of array 1 is D, right? It means this value, then -2 minus B, this one, then minus C, -3 here, and C. So this one will be, these two, A and D will be changed, and these two will get minus, right? So this is the adjunct. Then this one should be multiplied by 1 by -2, right? So inverse is equal to 1 divided by -2 multiply adjunct array, right? Then we can print it. Print inverse, we should get the same result, right? -2, 1, 1 minus 1, and 1.5, and -0.5. Then we can print eigenvalues. So eigenvalues and eigenvectors. Eigenvectors, we will get them using this function np.linalg ig. So this compute the eigenvalues and write eigenvectors of array, right? Then here we can print eigenvalues and also eigenvectors. So you can see here we get eigenvalues -0.0375 and eigenvectors. So in linear algebra, we learn how to calculate eigenvalue and eigenvectors. So if we have AV is equal to lambda V, then we call V as eigenvector and lambda as eigenvalue. And also in NumPy, we can solve the AX is equal to B, right? This is an equation. So in here, for example, we have a B vector is equal to NP array of 5 and 11, right? Then X is equal to, we call this solve function, right? So linalg np.linalgebra.solve. We will pass the array and we will pass B vector, right? So it means, so what is the A? A is 1 and 1, 2, 3, 4, right? It means 1x plus 2y is equal to 5, And the second one here, 3x plus 4y is equal to 11. So these are the right hand side. These are the b vector, right? So 3x plus 4y. So we want to calculate this system of linear equation, and using this one we can find it. X is equal to 1, y is equal to 2, right? So 1 plus 4 is equal to 5, and 3 plus 8 is equal to 11, right? So using this solve function, we can easily solve such kind of functions. Now we're gonna try random number generator. We wanna add some randomness. NumPy random module is great for simulations. We set a seed with random.seed for reproducibility. And here we may use like 42. This set the seed for NumPy's random number generator to 42, and this ensures reproducible random results across runs when generating random numbers, such as in simulation or data sampling. So let's try. In here, for example, we go for np.random.seed, and in here we pass, for example, 42, right? We set seed for reproducibility, right? That's okay. Then we're gonna create a 2 by 3 array with random values between 0 and 1. So rand underscore array is equal to like np.random and rand of, for example, 2 and 3. So you can see here, we can print it. In here, we have generated 2 by 3 matrix. It means 2 rows and 3 columns, and each value is between 0 and 1, randomly generated. If I run this one again, then I will get something different, right? Because this is randomly generated. In here, we can apply some distribution as well. For example, normal distribution. So rand r, and in here, I'm going to add numpy, and then in here, random.rand normal, right? It means it is normally distributed, right? So random array with normal distribution. So normally distribution is where mean is equal to 0 and standard deviation is equal to 1, right? So in here, we generated some random array with normally distributed. So if you print out this one, I can get some different values. So in here, the difference is we use here rand function, and in here we use rand n function. Then I can add some own array to select, right? So for example, rand underscore array is equal to np.random. Then here I'm gonna use choice, right? Choice. And here 1, 2, 3, 4, 5. Then I want to generate one 2 by 3 array out of this run, right? So the values will come from this list. So you can see here 5, 3, 1, 1, 5, 1. If I run it again, then I can get some different result, but this out of these values, right? The next topic here is statistical operation. NumPy is a data scientist's dream for statistics. We compute the median, standard deviation, variance, percentiles. We can do many things here. These functions help us to summarize data fast, so whatever it is, right? For example, I have a data of my data is, for example, mp.array, and my array is something, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if I print my data, I have these values 1 to 10 here. You can see. Now I want to find the median of my data, right? So print mean of data, right? First, let's try the mean of data. Mean of data, it means sum of all 1 plus 2 plus 3 plus 4 plus 5 is 55. Divided by 10, it is 55. Or I want to find out the median, right? The middle one, right? So print, then median is equal to np.median data, right? So median, it means the middle one. So how many data we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because it's even, the median is sum of 5 plus 6, 11 divided by 2, 5.5, right? Then I can find the variance of my data. So print variance of my data is np var of my data. This function var will calculate variance. So what is the sample variance? Sample variance is each data point minus mean square divided by n minus 1 for sample, and divided by n for the n, it means the number of data. Or I can print the standard deviation. Standard deviation is root square of variance, right? So root square of 8.25 is 2.85. Or I can print the percentile. So print quartiles. So to a quartile, it means 25%, 50%, and 75%. So it means we have this data, and if we divide in 4 quartiles, the first quartile will be 3.25 something here. Then the second one again. So if I add one more data here, like for example 0, right? 0, then we can easily see the quartiles, right? The first quartile is 2.5, this 50 quartile is 50, and 70 quartile is 70.5, right? This is how we can calculate the quartiles. The next topic is broadcasting. Broadcasting is NumPy's magic. Broadcasting let us operate on array of different shapes. We add a scalar to an array and it's applied to every element. We can add 1D vector to a 2D vector and it is applied to each row. So broadcasting keeps our code clean and fast, but we should check the shapes to avoid errors. For example, we have one array and the array is 1, 2, 3, 4, 5, 6, right? Then we have a scalar as well, a single number, and this one is equal to 2, right? So original array is this one, 1, 2, 3, 4, 5, 6, and the scalar is 2. The scalar is number 2, right? Now I want to broadcast the array and the scalar. It means I want to add a scalar to each element of that array, right? So print, then here array plus scalar, right? So you can see here our array is 1, 2, 3, 4, 5, 6 plus 2. 1 plus 2, 2 plus 2, 3 plus 2. So you can see here the result. Or for example, I have a vector and my vector is 1, 2, 3. Then I want to broadcast vector to each row, right? So print, then here I'm going to add array plus vector. So you can see here, this is 1, 2, 3, right? So 1 plus 1 is 2. 2 plus 2 is 4. 3 plus 3 is 6. Then again, 4 plus 1, 5. 5 plus 2, 7. And 6 plus 3, 9, right? This is broadcasting. We need to save our data or we load our data, right? For that one, we use save function to store array in a binary in .npy file, and we use load function to retrieve them. For example, here I have this array, the same array that we have here. So we have this array here. We want to save it, np.save, and here we can save it as a .npy file, array.npy file, and here we pass our array, right? So when I run this one, I can see one array.npy file here, right? Then I can load this one, right? So loaded underscore array is np load array.npy file, and I can print it as it is. Or I can say this one, I can save this one as a text file. So np.save and here text, then in array.text, right? And then I can load it. So if I run this one, I will see this .text file here, and then I can load it, right? So this is the loaded one, and I can print it, right? Print loaded array. So this is what we have here. The next topic here is structured arrays. Structured arrays are like mini databases. We define a custom data type with fields like name, age, and score. Then we create an array with mixed type. This is ideal for tabular data like CSV files or data sets with diverse types. So first, we define a structured data. For example, the type is equal to np.dtype, and here, for example, we have name, U10, age, I4, right? And also we can have, for example, here we add one more, and we have, for example, height as F4, okay? Now, this is my data. So in here, I define field like name as a string, then age as integer, and height as, for example, float, right? Then in here, I go for a structure array is equal to np.array, right? And I can add information to that structure that I have made, right? So for example, Alice 30 and 5.5, its height, Bob 25, age and height, right? Then this I created a structure array. Now I can print it, right? So let's try. This one should be array. So you can see here, Ali 30 and this one. So D types. So Ali 35.5 and Bob this one, okay? Now I can print and I can access name fields only, right? So print name column structure array underscore structure array name, right? Alice and Bob, only name here, right? Because here we have three fields, name, age, and height. Name, age, and height. Only I printed names, right? Or I can print only age, print age column only. So you can see here, this is the age column, right? 30 and 25. In NumPy, we can work with advanced mathematical functions. NumPy math functions are game changer. We can compute sine and cosine with like functions like sine and cosine. We can go for exponentials. We can go for logarithms and etc. These are vectorized, so they work on entire arrays at once, and they are perfect for scientific calculation. For example, we have angles, and the angles are np.array, and in here we have 0, pi by 2, pi is equal to 3.14, right? So np pi and again np pi 3 pi by 2. Okay, so these are the angles that we have generated. Then in here I want to print the angles, so print angles, and we print them, right? So you can see here we have 0, then pi by 2 is 1.5, then pi itself 3.14, and 3 pi divided by 2, 4. Okay, next I want to print the sign of these angles, print sign of angles. Then in here I use sign function, right? So see here, this is the sign of these angles that we have. Or simply we can go for print cosine of angles, right? COS, it will give you the cosine of angles, right? Or we can compute the exponential of each angle. Print, then here exponential of each angle that you can see here, 1, 4.24, and 111. Or we can compute natural logarithms for each one. So print can go for logarithms, and then here we will pass np.log, and in here one np.e and np.e2. Okay, now here I should add array, np.array. So 0, 1, and 2. The next topic here is masked arrays. Masked arrays handle missing or invalid data. So these are super useful for cleaning real-world data set with gaps or errors. For example, we have data of, like np.array, and our data are, for example, 1, 2, minus 999, and 4 and 5, for example, right? Okay, then in here, I want to go for mask elements equal to minus 999, right? So mask element np.ma masked values data and minus 999, then I can print it, right? Print this one. So you can see here, it will be masked. This one will be ignored. So we can see 1, 2, and this one minus 999 has been ignored, then 4 and 5, right? Or I wanna go compute mean, and I wanna ignore these masked values, right? So print then mean of masked data np.ma.mean of masked data. So it is 3. It means it will be 1 plus 2, 3, 3 plus 4, 7 plus 5, 12 divided by 4, 3. Right? This 99 minus 999 has been ignored. And the last topic here is Fourier Transforms. Fourier Transform is a core functionality in NumPy. It converts time domain signals into their frequency domain representations. If you have ever studied signal processing, you must be aware of Fourier Transforms. It converts time domain signals into frequency domains. And in this way, it enables analysis of periodic components in data, and this is widely used in signal processing and image analysis. So let's try one simple example. For example, we have t is equal to np dot lean space, and here from 0 to 1, we want to get 100 data, right? This is what we have. Then if I want to print t, so you can see here between 0 and 1, 100 number has been generated. Then I want to go for a signal. I want to create a signal with two frequencies, right? Signal is equal to np dot sign, then 2 multiply np pi multiply 5 multiply t, right? So this is a signal. The signal is 2 pi multiply 5t, okay, plus, and in here we will just add some 0.5, and then np sine of 2 multiply np pi 10 and t, right? So we have two signals. That's correct. Some error here. 0.5 multiply should be here. That's correct. Now Now I want to find the FFT, right? FFT underscore result is equal to np.fft.fft of the signal, right? And now we compute the frequency bin. So frequency bin is equal to np.fft.fft frequency. And here we're gonna pass length of t, then length of t, then here t1 and minus t0, right? That's correct. Then we're gonna print first 5 FFT values, right? Print FFT values, and in here we can pass first 5. So you can see here, this is the FFT first FFT that we have printed here. Or I can print the first 5 frequencies, right? Frequency and point up to 5. And you can see here, these are the first frequencies that we printed here. Okay, that's it for our NumPy deep dive. In this lecture, we have covered everything from arrays to Fourier transforms, and I provided several examples. NumPy is essential for numerical computing, so practice these examples and check NumPy documentation for more information. Thank you for watching. Please feel free to leave your comments below this video lecture. Hope to see you in the next video.